Okay, so I'll start then. Thank you for coming, and thank you for coming to the talk on Zoom as well. So this is a mini course on the so-called Bernoulli and K property, Bernoulli property and the K property. And based on the plan, the first thing that we wanted to discuss was sort of like a version of the Ornstein theorem. And I wanted to, before getting into this proof of the theorem, I wanted to give some broad comments. I wanted to make some broad comments, just to contextualize why the so-called finitary isomorphisms are somewhat relevant to the situation. So the talk is the Keane-Smorodinsky proof of Ornstein's theorem. Okay, this is readable. So it all starts with the famous isomorphism problem. When are two dynamical systems the same? And classically speaking, there were three different contexts in which people thought of this. And this is, for instance, in the context of Hanmusch's book, which is quite old. So you have, let's say, mu f, a bimeasurable transformation of a measurable space that preserves this probability measure, and yet another guy like this, mu g, acting on some other space, and you want to say that these two are equivalent. So the standard way would be to say that there's an x, there's a phi from x to y, such that phi conjugates f and g, and hopefully it's going to preserve the measure as well. So it takes this measure here to this measure there. So this is the strongest, in a sense. So this is the measure theoretical isomorphism. So measure theoretical. The second is you can look at whether or not the two automorphisms induced on the measure algebras are equivalent. So this is sort of the algebraic way. And certainly measure theoretical isomorphism implies isomorphism of Boolean sigma algebra autos. So if I have a set, of course, my transformation f, I can imagine to take it to its preimage. And so this induces an automorphism of the measure algebra of x. And you can say, okay, so is there a similar conjugacy this way? And then the third way was the spectral method, or spectral way. Rather, Koopman, perhaps, is better to say. Are the unitary operators acting on L2 unitarily equivalent? So one of the first major problems in ergodic theory was to be able to distinguish systems even when perhaps they were spectrally isomorphic. So one example for this is that very early on, people realized that any two dynamical systems that are that have countable Lebesgue spectrum are isomorphic, spectrally speaking. Early on, so let's say von Neumann and other people, perhaps, etc., realized if mu f and mu g have countable Lebesgue spectrum, let's not get into what this means, then they are isomorphic. Then they are isomorphic. They are spectrally isomorphic.
By this you mean that there's an isomorphism in spaces?
Exactly. Yeah, they're unitary operators. That is to say, i.e., there is a Hilbert space isomorphism from L2 of x mu to L2 of y nu, such that this equals this. The problem with this, or perhaps the genius of von Neumann, was that he realized, and other people realized, that possibly this is not the end of the story. Because they had this inkling that shift systems have always countable Lebesgue spectrum, but quite possibly they are not quite the same system. So shift full shifts. So full. Let me just write it like this. Full shift systems have countable Lebesgue spectrum, so they are spectrally isomorphic. But it seems like the shift on two symbols with one half measure should not be measure theoretically isomorphic to the one with three symbols and uniform measure. Okay. And indeed, 20 years later, this after this theory was established, Kolmogorov was able to come up with an invariant for measure theoretical isomorphism, and that was entropy. Sinai sort of modified it just a little bit, which turned the definition into the definition that we're using pretty much today. So this is the context. Entropy, so Kolmogorov, I guess it's also good to say, Sinai realized there is an invariant, and this is pretty much the only invariant actually. There's an invariant called entropy, for measure theoretical isomorphism. And that invariant associates, for instance, to the shift. So entropy associates to shift on n symbols with uniform probability, the number log n. In particular, the shift on 2 symbols cannot be isomorphic to the shift on 3 symbols. Now, this is sort of where where my part of the conversation or the presentation starts. The next question is, whenever you have an invariant, just as in invariant theory, the next question that you ask is it a complete invariant? Let me perhaps write it more explicitly as well. So the definition of entropy that we're going to be using, or the definition of entropy that the expression that the definition of entropy reduces to in our setting is what I was trying to say. So let me set up some notation. Let me take a positive integer, and a underbar is going to denote the set of a elements starting from 0. And let me put x to be the set of all, or rather space of all functions from integers to a. That is to say, this is the bi-infinite sequences using that you can write using the symbols coming from a underbar. And I have a shift operator. If I have a function, you just increase the index by 1. That is to say, if you have a ticker tape like this, so this is the x, this is the 0th coordinate, this is the first coordinate, and so on. The shift takes everything this way. So now the 0th coordinate is x1, now it's x2, and so on. If I have a probability measure on a underbar, then let me define P hat to be the product measure. Certainly this is preserved under my shift. And now we have systems. We have a bunch of systems. And these are the so-called Bernoulli schemes. Okay, so this is the main subject of interest, at least for the purposes of my talks. So I have a shift space, I have the shift transformation, and I have a certain type of invariant probability measure. Of course, these are not the only invariant probability measures on this. For instance, you have measures that are supported on periodic orbits. But this is sort of like a certain class of measures. That you have also Markov measures and so on. We're going to be focusing on this case. So once you have that, the invariant that Kolmogorov and Sinai constructed, entropy, turns out to be this. And I'm using the Gromov notation in a sense. Entropy of this dynamical system with respect to this measure is, and I'm also going to use this notation, h of p, which is the sum over I pi log 1 over pi. It's a finite number, possibly 0. Okay? And indeed, if you have the uniform measure here, this does produce you log n, where n is the cardinality of n. Okay. So now the question is Kolmogorov-Sinai entropy a complete invariant? And of course, as usual in dynamical systems, perhaps it's better to state this question this way. What is the largest collection of dynamical systems for which the Kolmogorov-Sinai entropy is a complete invariant? And indeed, people did this, and now they're called Ornstein systems. Because Ornstein was able to give this rather satisfactory answer, but of course not the end of the story. Ornstein says, for p hat sigma x systems, i.e. for Bernoulli schemes, the answer is yes. That is to say, two Bernoulli schemes are measure theoretically isomorphic if and only if their Kolmogorov-Sinai entropy is equal, is the same. Now, Ornstein actually did this for countable symbols, etc. as well. And you can go beyond Bernoulli. But for the purposes of my talk, we're really focusing on Bernoulli systems, so full shifts on finite many symbols with these types of probability measures, product probability measures. Any questions? Okay. Or maybe I should also mention these Meshalkin and Blum-Hanson examples. And these people were able to construct or were able to realize certain probabilities such that the full shift has the same entropy, but the systems themselves don't seem to be that it's not that clear that they're isomorphic, at least at the first glance. So maybe I should mention one example like that. Meshalkin and Hanson examples. For instance, if you look at this and this, so this gives you a system on 4 symbols. And if you look at this, 4, this gives you a system on, let me use B for the other one, on 5 symbols. Their entropy is the same. But it's not as clear if they're isomorphic, measure theoretically speaking. So this goes back to Meshalkin, and then Blum and Hanson sort of generalized as far as I understand, I wasn't able to look at the original paper because I don't think it is translated. And as far as I know, the Western mathematicians, let's say, only know of this example because of this paper, because in their paper they are mentioning this particular case. So maybe there's a translation though. I don't know. Okay, so it is still, you see, it's relevant. It's like I give you two systems, one on 4 symbols, one on 5 symbols. Their entropy, this number, you just compute it. It's the same. Are they isomorphic? Ornstein says yes, but it's not as clear how to construct it. So I gave you 3 different senses. Let me add a couple more senses, because that's what we're going to be dealing with. Okay. So we have measure theoretical isomorphism. This implies isomorphism on the level, or at the level of Boolean sigma algebras, which in turn implies isomorphism on the level of L2 spaces. We just saw that isomorphism here doesn't always imply this. Now we're going to go a little bit further. We have this invariant entropy, and it is a measure theoretically invariant. In fact, it is an invariant of a much weaker relation, and let me call this being a cofactor. So weak isomorphism. Because fairly early on, Kolmogorov-Sinai realized that if nu g is a factor of mu f, but this map is not necessarily it's not necessarily invertible, you can still talk about their entropies. You can still compare them. So not necessarily invertible. You can still say that the factor system has to have less entropy, which kind of makes sense because in order to obtain a factor, you're lumping things together. You're losing resolution, which means that your entropy should decrease, possibly. And so, of course, if mu g is a factor of mu f, and vice versa, mu f is a factor of mu g, their entropies would be the same. But people realized, and this did take a while, that two systems being factors of each other in the measurable category or measure theoretical category is not the same thing as there being an isomorphism between them. I think a student of either Ornstein or Rudolph was able to construct examples. This did take a while. So on the other hand, we can also realize that, maybe I should write it here, even though I'm considering these systems as measure theoretical dynamical systems, this shift is defined everywhere. And so I can say perhaps, and indeed it is a homeomorphism. It is a homeomorphism. So perhaps major theoretical isomorphism is, in a sense, asking for, so perhaps we can ask for more. That is to say, maybe we can ask for a homeomorphism phi from x to y that conjugates the two systems. Certainly, a homeomorphism, a topological isomorphism would imply major theoretical isomorphism. And let me write it like this. There's going to be another box here.
So when you say homeomorphism, you mean homeomorphism that also maps to store the measure correctly?
Yes. So, yes, exactly. That preserves measures. Yes. But even if you don't consider matching the measures, it turns out to be too strong. And I'm going to mention this in a second. And again, if I wanted, I could have said, I'm not even going to worry. I'm not even going to worry about the topological structure. Let me just ask phi to be just the bijection. The real obstruction here that phi is defined everywhere. That is the real obstruction, not that it is a homeomorphism. And this box, I'm going to put something in a second. But these are sort of all these different senses in which I can imagine the two systems to be isomorphic, conjugate to each other. So here is why this is too strong. That's an observation, and that's why we need this box. And I'm going to put here ash-topological. So this is a digraph that I keep using, sort of like an abbreviation for almost everywhere. And it's an Old English letter. It's called ash. For high-level stuff, it's fairly useful. Observation.
So by this you mean there is a settable measure for which it's conjugacy?
Yes. Let p hat sigma x and q hat sigma y be two Bernoulli schemes. Here x is on A symbols and y is on B symbols. Then we have these bijections. Then there are bijections. There are the following bijections, namely, first of all, bijection from A underscore to B underscore. Bijections from X to Y that commute, that is equivariant, if you want. Oh. And homeomorphisms. Okay? Because if I were to have a bijection between the symbols, this certainly defines a bijection between the shift spaces that commute, and indeed it defines a unique bijection, and that's going to be continuous as well, a continuous inverse. And on the other hand, if you were to have either one of these, you can realize that it would have to send fixed points to fixed points. Well, if it has to send fixed points to fixed points, the fixed points of the first guy is isomorphic or bijective to A underscore, and likewise for the other guy. So this is, in a sense, we can imagine this to be match the space of matchings for 0 cocycles of x and 0 cocycles of y. So this is too strong.
What do you mean in the second line? Space of bijections from x to y?
Yes.
So that's weaker or stronger than being homomorphic?
They're all isomorphic. Bijection that commutes with this is the same thing as a homeomorphism.
The last line implies the second line is easy for me to see, but not the second line. Every homomorphism is a bijection.
Well, going from 2 to 1 is, how is that? Because if you have this, well, just look at the fixed point of. So if you have a bijection, any fixed point of sigma x has to be sent to a fixed point of y. So any bijection here induces a bijection on the sets of fixed points of sigma x and sigma y. Well, the fixed points of sigma x, for instance, is in bijection with a underscore.
Okay. But the arrows, yeah. Okay.
Yeah, I mean they're all some like they're all bijective. Maybe I shouldn't. They're all the same sets. The point is that it's not really the homeomorphism. It is the fact that these pi's are defined everywhere. That is the obstruction. So now you're asking for the next best thing. Give yourself a zero measure room. Right? So this clearly is too strong. So ask for this. So you see, in this case, I'm not even asking for the measures to be preserved, but certainly it will be preserved in this case, up to a permutation. So that's why you look at functions that are continuous of a set of zero measure. So the real obstruction is that the conjugacy that we were looking for in the categories that are stronger than measurable are defined everywhere. So definition, let's say x and y be, for simplicity, compact metric spaces. I think there would be enough. Compact metric. So a partially defined function let me also choose measures. A partially defined function phi from x to y is ash continuous if there is an x naught in x, there is a y naught in y of full measure, each full measure. I'm just going to write it like this. Up to mu, x naught is the same thing as x. Up to nu, y naught is the same thing as y. And phi restricted to its domain inter x naught I don't want to write it like this. Such that phi is defined on this, and is continuous and matches the measures.
You wanted to be homeomorphism?
No, this is just a continuity. Just like in weak equivalence, I'm just first looking at the or asymmetric relation. If I have such a function that has an inverse whose inverse is also ash continuous, I'm going to call it an ash-homeomorphism. Can erase this. If phi is an ash is ash continuous, and has an inverse, that is ash continuous. Let me just write ash C0. Then call phi is called an ash homeomorphism. And just like in the weak equivalence case, it doesn't necessarily mean that if you have an ash continuous map from one system to another, and vice versa, they have to be ash isomorphic, ash-topologically isomorphic. But certainly, if you have a homeomorphism that conjugates the systems, you have an ash homeomorphism, assuming that you have measure preservation. And certainly, if you have an ash homeomorphism between two systems, they are measure theoretically isomorphic. And in particular, entropy is also an ash topological isomorphism invariant. And Keane and Smorodinsky was able to prove that indeed, for Bernoulli schemes, it's a complete invariant. Kolmogorov-Sinai entropy is a complete invariant for Bernoulli schemes in the context of ash topological context of isomorphism. And this is the topic of my talk. Finally, I was able to give it. So any questions so far?
Just have a comment that you can get not almost everywhere topological isomorphism, but a large set of topological isomorphisms that lose them, right? So this
Yes.
losing to sets of full measure rather than almost full measure.
Yes.
Once you have a measure theoretic isomorphism.
Yes, yes. But this is also sort of like a thing in, for instance, piston theory. The isomorphism that Lucien would produce would be abstract.
Yeah, Yeah.
You don't have any control over it. This one is very controlled. It's a very explicit, they're just like stitching the two systems one step at a time. It's very explicit. And it's fairly elementary, the method. And to some extent, it can be generalized as well. But let me just mention a couple of things then, some remarks. This is sort of like the theorem that I'd like to discuss in the rest of this talk and the next two talks probably. So here are some remarks. First of all, the Keane-Smorodinsky proof is fairly elementary. I mean, they're being very smart with how they're doing things. But essentially, all they're using is the standard Shannon-McMillan-Breiman theorem plus some combinatorics. And there's some associated logistics underneath all this. So let me just write that as well. So that's good compared to Ornstein, whose proof is very involved. But at the same time, this is sort of like a double-edged sword because their method is fairly limited in scope. Compared to, for instance, Ornstein theory, which is sort of like a whole theory that builds these tools called, distinguishes these properties that are checkable for a wide variety of systems, weak Bernoulli property, very weak Bernoulli property, etc. This is fairly limited. People are still trying to generalize this to some extent. Even Rudolph, people like Rudolph, has some work on this, but it is limited in scope. So it's a trade-off. And perhaps it would be good to mention Katok has a survey on entropy theory, 50 years in entropy. He does have some remarks about this. The point is that this ash-homeomorphism, if you want to do it in the smooth category, for instance, it's going to depend on the partition. It's going to be messy. So it's not really sort of like an invariant that would be applicable for broader systems. Whereas Ornstein theory, right, for smooth systems, if you want to show exponential mixing, implies Bernoulli, you just verify weak Bernoulli property, and you're good to go. Of course, in order to do that, you need to be very good, but can be done. Elementary proof, limited in scope. So I'm going to say something else. And on the other hand, of course, compared to Ornstein, it is telling you more. It's telling you something more specific. Specific construction. Specific construction. Construction. Sharper consequence or sharper conclusion. Which is expected, right? It's like if your scope is limited, it is likely that you have more properties, which means that you can say more things. Okay, so these are the three remarks. Any questions? Now, I'd like to mention a couple of things before we wrap up for today. I'd like to mention a couple different characterizations for ash-homeomorphisms in the context of Bernoulli shifts. So in the context of Bernoulli schemes, it just means that essentially your isomorphism is completely determined by what it does to finitely many entries, as opposed to looking at sort of like the whole shift, which is very similar to how you look at locally constant functions, right? It's like it's the same thing. Locally constant closed cycles, etc. It's the same idea. Yes.
I'm wondering, except for Bernoulli schemes, are there any like complete invariant or dynamical systems already known?
For all dynamical systems?
No, like for specific dynamical systems. Is there any like example of complete invariants? Like
So yeah, for like non-uniformly hyperbolic systems, entropy is also invariant. But zero entropy is wild. You won't get it by much. I mean, you have sort of the opposite with rapid rigidity, right? They're isomorphic only if they're algebraic isomorphic. So you can actually prove that it's very rare to find invariants with zero entropy world. So this is the tension between the two. The high entropy world is very complex, but there's not very many invariants, whereas the low entropy world has low complexity of the dynamics, but it's very difficult to find invariants in systems.
But in the context of algebraic, you have the spectral tools available to you too. And in a different context, for translations on compact abelian, they have discrete spectrum.
True. But four-cycle flows, for instance, have countable.
Yeah, I understand. But for some algebraic systems, spectral is still sufficient, for instance. But yeah, so the main, I think, push is that even if it's not entropy, it's going to be something like entropy. It's going to be maybe pressure, blah, blah, blah. A couple different things. There, like underneath all this, I think there's a homology theory hiding, because entropy is a homological. It's like a dimension-like thing. Dimension-like things are homological. But it's not quite easy to see what should be the thing.
Are the Zoom participants able to hear our discussion?
They can hear me.
Yeah.
Well, yeah, no, I don't. I mean, maybe much more muted. Yeah. Okay. So characterizations. So in the context of I'm not going to write it actually. I'm gonna discuss this characterizations of ash-homeomorphisms next time. The vague idea. So let me just write it like that. For ash-homeos between Bernoulli schemes, think of, let me just write it like that. Think of locally constant. Or you can also write it like this. You can say homeomorphisms that are determined by finite codes. Determined by finitary code. And because of this property, indeed, in this context, people also call it finitary isomorphism. Another word for ash-homeomorphism is finitary isomorphism. Another word is almost topological isomorphism. So let me write that too, probably. It's good. is the same thing. Finitary isomorphism, which is the same thing as almost topological. Perhaps it would be also good to mention whenever you have an whenever you have an ash-homeomorphism that support x naught and y naught, you can make it so that they are residual as well. So not only are these functions, are these homeomorphisms defined on large sets in terms of measure theory, but they're also defined on large sets, on sets that are large in terms of topology. And there's again sort of like an algebraic interpretation of this as well. I'm going to go into this more in detail next time. Let me also briefly mention the outline. And we'll be done for today. So, outline. Step 1, markers. So somehow you look at the probabilities in the two systems, the probability vectors, and you say, okay, I'm just going to look at one of their components that contribute, in a sense, the most to entropy. You say that I'm just going to match them up. So first you have here p hat sigma x, q hat sigma y, and once you have that marker, you define another shift, another Bernoulli scheme by lumping all the other components of the probability vector that contribute to entropy lesser. You lump them up, and that gives you a Bernoulli shift on two symbols that happens to be a common factor. Okay? Second is to say, okay, I match this and this along this guy. So so you're trying to build your isomorphism like this in a way that is preserving the fibers. And the fibers are what are called fillers. And this, you're using this to handle this, they are defining something called a skeleton. These are essentially binary sequences, binary finite words in two symbols that are of this form. So you have a bunch of kisses and hugs. Okay, so this part, for instance, corresponds to the marker, and just like, you know, this sort of like reminds me of genes and all that stuff. So you have sort of like a large number of markers that tell you, okay, this is where your skeleton starts. And then in between, you can still have markers, but their lengths can be cannot be as long as this. So you're sort of like marking the beginning of a skeleton and the end of a skeleton by putting a lot of the markers. And x's correspond to the probability, so to the components that are to the components of the probability vector that contribute less. Then you use combinatorics. Let me write it here. using this Shannon-McMillan-Breiman theorem and combinatorics in particular, more specifically, rather, you're using a version of the marriage lemma to match filars. And then you do, you sort of like start stitching these two systems one step at a time, essentially. You're taking longer and longer skeletons that are compatible with each other. And on each skeleton, you're sort of like either going from here to there or from here to there. Essentially, there is a joining here that tells you how to do it. And let me just try that. The fourth step is that using this joining, you're doing sort of like, just like in the Riemann rearrangement theorem, you go sort of like over and under, over and under. That's essentially the idea. But this is the outline. Next time, I'm going to start with characterizations of ash-homeomorphisms in the context of Bernoulli shifts. And then we're going to start going more into detail. Any questions?
I suggest we give Rob up around the before he asks questions.
Oh, yeah, thank you. Yeah, if you, yeah.
All right.
I guess not.
Let's give another
Okay.
applause.
Yeah, thank you for coming. Good. Shall we start, or shall we wait a couple more minutes?
I'm always a believer in starting on time.
Okay. So, hello, and thank you for coming. Thank you for being on Zoom. So this is the second part of my lectures on the Keane-Smorodinsky proof of the Ornstein theorem. I should mention that if you're watching this on Zoom, I'm aware that the visuals are not as crisp. I sort of like made a trade-off. I wanted more space, and I had to lose focus a little bit. So let me remind you the setup and the notation. I have A, B, positive integers, and let me use A underscore for the set with A elements from 0, and likewise for B bar. And then I have X, which is the set of bi-infinite sequences that can be written using symbols from A, and likewise for Y. If I have a probability on A, let's call it P, then let me denote by P hat the product measure defined by it. So this is a measure product, this is a probability measure on X. And likewise, if I have a Q, that's the probability measure on this finite set, then I have Q hat, which is going to be the product measure on Y. I have a dynamical system, which is a shift on X and likewise on Y. And so I have P hat sigma X on X and Q hat sigma Y acting on Y. And we had the entropy, the so-called Kolmogorov-Sinai entropy of this type of maps. These are called we call Bernoulli schemes. The entropy of this is also the H of P, which is defined as this sum. And the Ornstein theorem said that P P hat sigma x is measure theoretically isomorphic to Q hat sigma y if and only if the entropies match. We discussed how this implies this last time. This was how, or why, one of the reasons why Kolmogorov defined this notion of entropy as an invariant. And we defined this more strict notion of isomorphism for dynamical systems, which is this ash-topological isomorphism. And Keane and Smorodinsky really showed that if P hat sigma x is isomorphic in the sense of ash topology to Qy, this is equivalent to the entropy being the same number. And recall that I was using this symbol, ash, to denote almost everywhere. And perhaps I should write that down because that was one of the things that I had promised I was going to go more into detail. Let xy be compact metric. Mu and nu be probabilities. And let's say that we have a partially defined function from x to y. I call it ash continuous. If there are full measure subsets, x0 and y0, such that when restricted to this, x0, with respect to the subspace topology, it becomes continuous. To be more rigorous, I should be worried about the domain of this function, and I should be taking the intersection of x0 with the domain and blah, blah, blah. But let's not worry about that. And if I have an ash continuous function whose inverse is also ash continuous, that's called an ash-homeomorphism. Now, in the context of shift spaces, so this can be made sense for when you have a bare space, or if you have a certain partition fixed on your standard space. You can again make sense of this. And it will be important for us. Observation. In our setting, so if X is the space of bi-infinite sequences with symbols coming from A under bar, and likewise for Y, then mu any shift invariant measure on X and nu any shift invariant measure on Y, probability. And let's say that I have a function from partially defined function from X to Y, then the following are equivalent. Y is ash continuous. 2, there's a measurable function, j, let's call it, on x, taking integer values, such that for almost all x in x, let's call it x star, for almost all x star in x, let me write it like this. For almost all x star in x, if for all I less than j star, and for all x in x, if the ith entry of the set or of this sequence matches with the one that you chose, then the 0th coordinate of the image of this point matches with the 0th entry of the image of x star. So you have a map phi taking sequences to sequences, or ticker tapes to ticker tapes, and in order to be able to read the 0th coordinate, or any finitely many coordinates, of the image of a sequence, or of a point, all you need to do is to look at finitely many entries in the image. This is one way of saying this. So perhaps I should write it like this. Let me just compress all this. For almost all x star in x, 0th coordinate of the image, when restricted to the cylinder set, to these entries, put the appropriate entries coming from x star. So this is a cylinder set. And I'm looking at the 0th coordinate. This is constant. Okay? So this is the second way of thinking about it. The third way of thinking about it is this. I should say here. And this is a semi-conjugacy. Otherwise, just looking at the 0th entry will not work, will not be sufficient. The third entry is that for all, let's call it I in B, if I were to look at an element of the standard generator of Y, which is a cylinder set, and if I were to look at its pre-image, there's a countable collection, C sub I of cylinder sets of X, such that up to a measure mu, the pre-image of the cylinder set defined by putting the ith symbol, so the symbol I, to the 0th coordinate, is the union of the CIs. C and CI, C up to a measure mu. Okay, so this sort of like is perhaps useful in the context of the specific shift spaces. The third characterization is useful in the context of when you have dynamical systems on standard measurable spaces with fixed generators. And you just open up the definition. of course, if I didn't put here this shift invariance or shift equivariance, instead of saying I need just one measurable function, I would need to say that for all finite subsets of spaces, I need a measurable function that does this. The fact that this is shift equivariant means that this just tells me that I can get any finite code for the image by looking at finite mini codes in the entry, or in the input. Okay. So any questions about this so far? Yes. Oh, okay. So we're gonna move on. So this is sort of a nice way of thinking about this. I would like to say a couple words about something. So here this J is an important thing. So this function, so there is such a function if you have ash continuity, and if you have ash homeomorphism, if you have an ash homeomorphism that conjugates the two actions, then you also have that the inverse, for the inverse, you also have another J that is quite possibly a different function. And then you look at the least J measurable function that does this, and that gives you the so-called coding length function. Okay. So J tells you, so minimal J is the minimal number of entries one needs to read to determine the 0th coordinate of the image. Coordinate and let's call this minimal J the coding length function. It turns out that in the case of the Keane-Smorodinsky isomorphism, we do end up constructing an ash homeomorphism between the two shifts. But the coding length function of that is never going to be L1. So this is by Parry. And I'm just going to call it J again. The J of the Keane-Smorodinsky phi is not, well, is L1 if and only if, in fact, Q is a permutation of P, which is a trivial case. Q is a permutation of P, which, like we discussed last time, is if and only if, in fact, there's a homeomorphism that is defined everywhere between the two shifts that takes the measure to the measure. So this is like too strong, as you see. What is interesting is that, so there's behind us like a cohomology equation, and Parry is able to find, it turns out that there is something called the information co-cycle, which is like something very natural from an entropy theoretical point of view. And these two are functions. You're thinking of them as potentials. And Parry figured out that the two information co-cycles of the two systems being cohomologous is equivalent to the systems being ash homeomorphic. And then the transfer, the regularity of the transfer, ends up being related to the regularity of this J function. In this case, if the J function is L1, then the information co-cycles end up being homologous with a measurable transfer, bounded measurable transfer. If it's if it's in Orlick space L log L, then it becomes something else, and so on. So it's very interesting. What is further interesting is that Serafin verified a claim that Keane and Smorodinsky made back in the day. After 20 years later, they made that statement. The J function of the one-sided Keane-Smorodinsky map. So I'm not looking for ash-homeomorphism. I'm looking for an ash continuous map from one to the other one, and yet another ash continuous map from the second to the first. This is sort of like the analog of the isomorphism. The J function of the one-sided Keane-Smorodinsky semi-conjugacy is L1. And so this was a claim stated as a theorem without proof by Keane and Smorodinsky back in the day. And this is like super interesting as far as I'm concerned. And there's a lot of further work about invariants of ash-homeomorphisms or ash equivalences by Schmidt, Tunjal, and other people. Very interesting stuff. So any questions about this? So this is a broad way general way of thinking about it in terms of topologies. This is sort of like a more explicit way of thinking about it. And it turns out that this J function, the coding length function, has further structure that tells you something about the regularity of solutions of the cohomology equation, or some cohomology equation. Let's put it this way. So, okay. So now I'm going to start talking about some other thing that we're going to need, some combinatorial stuff that we're going to need. That sort of like comes into play toward the end of the proof. But I think it would be good to introduce them early on, because that's sort of like the one of the big parts of the proof. One part of the proof is the Shannon-McMillan-Breiman theorem, or being able to apply it in a nice way. And the other part is to be able to handle the combinatorics. And so Peterson calls this sociology because it's all about these maps called societies. I'm just going to call it combinatorics. So this is associated to the marriage lemma. Societies, and let's also write couplings. So I'm going to start with two finite sets. Let's just set that aside, what we've discussed so far. Let A and B be finite sets. Alpha be a probability measure on A, beta be a probability measure on B. I'm going to call a map a society, and I'm going to denote it like this. S from A alpha to curly arrow, B beta, is a function between the power sets. So collection of subsets is a function such that a couple of things need to happen. First of all, I need to have a splitting property for all E, a subset of A. S of E should be the same thing as the union of S of A, where A varies over E. Second of all, you need to have some sort of very strong absolute continuity property. That is to say, for all E subset, measure of E should be dominated by the measure of its image. Okay. So property 2 is strong, that's how I imagine this, strong absolute continuity. And property 1 is telling you that in order to define a society, you don't need to look at this power set of A. You can just say, I have a family of subsets of B parametrized by elements of A. That's sort of a way to think about this. Another way to think about this is to think of them as sort of reverse hash functions, if you want. So S of A, I'd like to imagine as all those elements of B that I would hash into the bucket named A, and so on. And yet another way of thinking about this is where the name marriage comes from. You're sort of imagining A to be the set of boys and B to be the set of girls. And for A, a boy, S of A is the collection of all the girls that A likes. That's sort of like the interpretation that Peterson gives. And this is sort of like a very classical combinatorial stuff thing. I'm not going to use this intuition that much. It confused me more, so I just left it alone. So this is this. There are a couple sort of associated constructions. If I have a society, then I have the dual society, which I'm going to denote by S star. It goes from B beta to A alpha, and S star of B is the set of all those A's such that S of A contains B. Refinement, if I have two societies from A alpha to B beta, I'm going to say that R refines S. And I'm going to denote it like this, R arrow S, if for all A and A, R of A is a subset of S of A. Perhaps I should mention this. If you were to plug in here E equals A, this is going to be 1, which means that the image of any society is going to cover. So this is sort of like a certain type of covering. What else? Refinement. Okay. Collision number. This is also called the promiscuity number for a society. If I have a society, its collision number also called the promiscuity number, is this. I'm going to denote it like this. Gamma of S equals the number of B's such that the cardinality of S star of B is at least 2. Okay? So just to open this up a little bit, so this could happen only if you have 2 points, A1 and A2, that are not the same in S star of B, which means that B is covered, B is included both in S of A1 and S of A2. So this is S of A1, this is A2. So in a sense, this subset collides with this subset, at least here. So that's why I call it the collision number. And the marriage lemma is telling you something about being able to refine societies in such a way that this becomes nice. Okay. Examples. One example comes from couplings. I think this is sort of most natural ones. But it is not true that all societies are defined by couplings. Let me just define what a coupling is. So let's write it like this. Example. Let lambda, so I fixed A alpha and B beta. Let lambda be a probability measure on A times B. I'm going to have some assumptions here, but let's define S sub lambda from A to power set of B by taking A to all those B's in B such that lambda of A, B is positive. I'm going to put here assumptions. If something happens, then this is going to be a society. If this, then S sub lambda is a society. In order for S to be a society, I'm just going to first do this. Oh, yes. Yes. Exactly. Yes. Yes. Yeah, so if you want to think of it this way, societies are generalizations of joinants. In this case, for now, we're looking at finite, so we're looking at maps between finite sets, but the reason that is happening is because we're going to take this machinery and plug it into the proof. And then because this is sort of between finite sets, it's going to help us build the isomorphism that is shift invariant. That's sort of like the idea. But yeah. So I'm going to first do the proof of this example, of this statement, and then based on the proof, I'm going to write down the assumptions. If I have a subset E, what I want is that I want S of E in measure to be larger than alpha of E. Okay? So let's try to open this up. I can write this like this. So this is the sum over all those B's in S of E of beta B. But then let's say this happens. Push forward of lambda to B is this. Let's say that if I were to push it forward, the weights that this push forward associates to any element in B is less. So that's going to be my first assumption. For all B in B, this, let me also perhaps write down what that means. So the space of, so the category of measure spaces does not admit products, and that's sort of like the main issue here. You're sort of like somehow using the categorical pathology to do things. So I have here A times B with lambda, and I have the product, I have the projection to A, and if I were to push forward lambda, I get a measure here, and I have likewise here another guy. And this measure, for instance, is just the marginal, right? It's like you take the sum over all B's of lambda of AB. The picture is that, so this is A times B. This is A, and then this is B. You have here a point, A, and in order to figure out what the push-forward measure gives in measure to this, you just look at the fiber and add all the densities up. And likewise for this guy. Okay? So I'm saying that if instead of equality, I have inequality, this is still true, and then this is equal then to this, but then you see, so this is the integral of, or the measure of A times S of E. But then this is a superset of the graph of lambda, if you want, AB, such that B is in S of, oh, sorry, A in E, B in S sub lambda of A. So I forgot lambdas here. So by Fubini, I can change it to, let's call this gamma. Gamma sub lambda of E. So this is lambda of A times S sub lambda of E, which is like this. But then, if I were to fix a point A, B is in S sub lambda of A, if and only if the measure is positive, lambda AB. But then I can just contain the whole fiber. So this is, in fact, really lambda of what am I trying to say here? Oh yeah, sorry. So this is like this. Sum over A in E and B in S sub lambda of A. Okay, but then this is the same thing as lambda of E times B, which is the same thing as, oh wait, here's what I need. Okay, so now at this point, I want to use the other one and write it like so. B in B alpha, oh, lambda AB, and then this is the second marginal. Okay. Push lambda to A of A. So here I need, so this is equal actually. And then this, I want to dominate alpha of A, so that the second assumption is that if I were to push lambda onto B, onto A, it should dominate alpha. So if my probability measure is such that if I were to push it onto the first guy, I'm dominating the internal measure, and if I were to push it onto the second guy, I'm dominated by the internal measure, then the map S sub lambda defined as this thing becomes a society. In particular, if it were the case that I have equalities here, that is to say, if my lambda was a coupling of alpha and beta, then I would have a society. Okay. Okay. So, any questions about this? This took longer than I thought. So, let me call any probability measure lambda that satisfies these two things a subcoupling lambda is a subcoupling of alpha beta if this happens, and coupling if you have equality. So that here you can replace this by alpha and that by beta. Okay? So we know how to write, how to come up with couplings or subcouplings. This gives you many examples of societies, but not all societies. Probably most societies are not induced by couplings or subcouplings. You can just do a combinatorial argument to see this. But this is that. Okay, so this is an important thing. Let me say more things about societies and their structures. Observation. Oh, wait. So now that I said this, societies versus yes, I can define product. Oh, before that, I should do this actually. Sorry. Observation. If I have a society then there is a coupling lambda of alpha and beta there's a subcoupling, let me be safe, a subcoupling of alpha and beta such that the society defined by the subcoupling is defining S. So basically you start with a society, you can sort of get rid of points, get rid of collisions, and eventually you get a subcoupling. And this is sort of like an interesting thing. If I have time, I might get into the proof of this. This is nice. And slightly more trivial is if t is a function and there's a coupling, there's a society, and there's a society yes. So I think that this comment is about the product is not defined by heuristics. Oh yeah, so I did not understand the comment about the products of probability spaces. Was this essentially that space of probability measures on a product of spaces is not equal to product? Yeah, so you can always take the product measure that would satisfy this, but in general, there are many more measures on the product measurable space. So it's an admissible measure that fits into this graph or diagram, but it's not the the product. So in order for this to be, so this category to admit products, there should be a unique measure here. But that is not necessarily true in general. And that's sort of like the issue. So when that happens, you call things disjoint, for instance. That's sort of like a rigidity. Yes. Yeah. So if I were to take two measure spaces, there's no natural way to take their products, actually. So it's not, so the product measure is not a natural product, I'm trying to say. There's a society S from A alpha to B beta such that S refines T. So if I have any function T from A to the power set of B such that it is refined by some society, then T is also a society. And perhaps I should mention one other example to sort of like think of this constructively speaking. If I were to define a map like this, S of A for any A equals B. It's everything. So this is sort of like, this is trivially a society, but there's a lot of collisions in it. So you start excising collisions. As you keep excising collisions, eventually, I'm claiming here, that you reach a refinement that is in fact induced by a subcoupling, and then you can make it into a coupling. And vice versa, if you were to have a society, if you wanted, you could keep adding more points into its sets, and eventually, so whatever you add, extra you add, it's still going to be a society. So the point here is that there's going to be, given any society, there's going to be a minimal refinement, such that if you excise one more element, for instance, you end up losing the property of being a society. So this is going to be important in the marriage lemma. And in fact, let me also mention that. So now the marriage lemma. Let S be a society from A alpha to B beta, then there is, oh, this is in fact if and only if, then there is a refinement R, let me put it like this. Then there's a coupling lambda of alpha and beta. It's not unique, such that the society defined by it, first of all, refines S, and second of all, its collision number. Yes. No. There's no uniqueness. And second of all, I think, so it has something to do with this procedure that you use to go from a society to a coupling that would define it. So there is some sort of choice involved there, and that's why it's not unique. S of lambda, then there's a coupling lambda of alpha and beta such that the society defined by this coupling lambda refines S, and its collision number is bounded by the number of elements in A. Okay. So if alpha and beta were standard uniform measures on finite sets, that gives you the standard marriage lemma that I mentioned earlier. Yeah. Okay. So when we're building this isomorphism in the Keane-Smorodinsky proof, what we're going to do is we're just going to say, okay, from the first guy, there's a society to the second guy. So there's a way to associate certain finite sets. These are called the filler sets of the spaces, of the shifts. We're going to say, okay, I'm going to take a society from certain filler sets to certain other filler sets. And then this machinery, combinatorial machinery, allows me to get a nice refinement of it that does this. And we're going to keep doing this for larger and larger finite sets that eventually cover almost every point in my space. And then because at each step we're doing this over finite points, finitely many points, this is also going to be shift invariant at the end of the day. So this is sort of like the idea. Like 6 or 7 minutes. I think, so okay. This, that, okay. I want to say a couple words about the proof of this statement because I think this is sort of the interesting thing here. And then I'm going to state one thing that reduces what we're trying to do to a specific case. Okay. So observation this. Proof or sketch of proof. So first of all, how to do this excision thing? First of all, I need, if I start with a society, I need first to be able to refine it in such a way that the collisions are bounded. So say there are 2 points, distinct points in A, and there are 2 distinct points in B, such that this happens. Okay? So you see, this would increase the number of my collisions. I want to decrease this. The way to do this is this. So this is this subset of B, and this is this other subset of B. Just going to draw Venn diagrams. And based on what I wrote here, I have one point here, B1, and another one, B2. So I'm going to define these functions. Oh, I have here. Take A, so S of A, if A is not AI, and take it to S of AI, take away BI, if A is equal to AI. So that means that, for instance, my R sub 1 of A1 is going to be the same thing, except avoid B1. So this guy is now this. Okay? And this is going to be everything. And likewise, I have another one, R2. There's R1 and R2. Both of these clearly refine S, but possibly they are not societies. But the observation is that at least one of them is a society. You say this is not a society. This means that alpha of some subset dominates beta of R1 of that subset. And using this, some combinatorics, very basic measure theory arguments, you realize that the other one has to satisfy the society property. So that's good. That allows you to excise one point at a time from your society to reduce the collision number. And eventually, you keep doing this sufficiently many times to reduce the collision number in total to a certain number. 3 minutes. So let's just say this. This is the idea first. So there is a, then there's a society. I'm going to apply it to something else actually. So let n be an integer. Define this new set b sub n, which is going to be b times n upper bar 1 to n, or under bar, it doesn't matter. Beta sub n is going to be a probability measure on the set. I'm just going to define it to be beta in the first one and Haar measure or uniform measure in the second one. I'm just going to take the product measure here. So beta of b divided by n. And I'm going to have S sub n from A alpha to Bn beta n. Take A to the product of S of A times the whole second component. Applying this excision procedure, there is an Rn from A alpha to Bn B beta refining Sn such that with a low collision number. Let me just write it like this. Okay, so now define lambda n, a probability in the product by this. So this is a subset of b times n. I'm looking at vertical slices. I'm taking intersection, and I'm looking at how many of this finite set, this particular set hits. That defines a probability measure, and then you realize 3 things. One of them is that for all, so it's a probability measure first. Second of all, we have this. So this dominates when you push forward. Second of all, this also dominates like so. But also, because of this refinement having nice collision numbers, reduced collision numbers, I also have an upper bound here. And it's exactly, so I can make it such that I have this bound. So this is a collection of, this is a sequence of probabilities. Take a accumulation point of them. In the limit, you have a lambda accumulation point lambda. In the limit, you're going to have lambda such that the B marginal, B push forward, is equal to beta. A push forward dominates alpha. But you can also realize that, in fact, it is equal. Note, so observe that lambda is, in fact, turns out to be a coupling. And certainly, if and it's also an observation that S sub lambda is going to be a refinement of your original society. Okay, I think I'm out of time. I was able to discuss the main combinatorial part. Next time, hopefully, we're going to start going more into detail with the proof. Thank you so much for listening. Thank you. Yeah, do we have any questions? Yes.
You mentioned that Parry introduces sort of cohomology theory.
Yes.
I mean, what kind of cohomology theory?
I mean, it's a standard cohomology theory that you use in dynamics. But let me say a couple. So, and this is not a theory that Parry himself introduced. This was like known for quite a while. It was known, probably von Neumann knew it, perhaps in the context of unitary operators and stuff like that. But so how do you compute the entropy of a map with respect to a measure? You say, I'm going to first take a partition, let's call it alpha, of my space. And then I'm going to, so this is a certain value, and then I'm going to look at the maximum of this. So what is this? So the way they define this, so if you have a finite generator, this tells you, and so for instance, it was realized fairly early on that for instance, Bernoulli schemes, there is such an alpha such that you don't need to take the supremum. So you can just compute this value. And what is this? Want me to define this as this entropy of this. So I'm taking alpha, and then I'm refining it. So typically they use this notation for this. I'm using more categorical notation. And then I look at where elements go in one time and second time and so on. And then you can also realize that you can, given any partition, there's an information function associated to it. And indeed, this entropy value is the same thing as the integral of a certain function, L1 function, which is the information function associated to this partition. Let me call it R f z positive of alpha Now, there's an alternative way of computing the entropy, which is by way of using the conditional entropy. And what you say is that entropy is the amount of information that you get today if you knew of all the future. That is to say, this is equal also to to the entropy of alpha given the future. And again, this can be written as an integral of the conditional information function. Okay? This is the information co-cycle. So this is an L1 function. It's an LP function. Let me just call this I. So I is the information co-cycle of mu f alpha. So this makes sense if you have a marked generating partition. And I can imagine this. So this is a certain conditional, right? So let me just write it like this. If you have this, this is the same thing as A in alpha chi of A of x, chi sub A of x, such times log of 1 over conditional of chi sub A conditioned on the sigma algebra generated by beta. Okay. And then when you sort of take the integral of this with respect to mu, it will generate this specific thing, which is the entropy. And so now we have I of p hat sigma x here, and likewise I of q hat sigma y from y to this information co-cycle of the first system, information co-cycle of the second system. But then, of course, I can pull it back if I had an ash-homeomorphism. So now I have this. And so you call two functions cohomologous. So I want these to be cohomologous. So let me write it like this. FGHI. Okay. If there is FGHIK, another function such that G equals minus SF, yes, minus K, up to a mu measure. This is sort of like this is modeled after group cohomology, if you want. Yes?
K minus K equals with
Yeah, that's a co-boundary. Yeah, I can write it. Yeah. You can do this because in this case, the coefficients are abelian, but in dynamics, of course, we're really interested in non-abelian coefficients. I mean, sometimes you are interested in non-abelian coefficients, in which case you cannot write it like this. But in any event, so you see, people say that G is cohomologous to F by so with K as a transfer. But of course, we have different regularities. The better this K is, the stronger the equivalence. So what I said there was that if your code length function, if two shift systems are ash-homeomorphic, then their information co-cycles are cohomologous with a measurable, bounded measurable transfer. And he also computes that for Bernoulli schemes, this cohomology equation never holds. Unless the probability vector of the first guy is a permutation of the other one, which is a trivial case. Are there other questions? And also people in the chat. Yeah. Yeah, if you want to sort of like, if you're interested in these kind of things, probably Zimmer's book is the best way to start. Zimmer has a book called the Ergodic Theory, semi-simple Lie groups or something. It's like, yeah. He has something, he has a theorem called co-cycle superrigidity. It's related to this. Let's thank out. Yes, thank you. Should I start? That would be fantastic. Yeah. Okay. Yes, there's no one on Zoom. Thank you for coming. So this is the third part, the final part of my presentation. I hope to do as much as possible, but there's still plenty of stuff that we ought to discuss. So I'm going to do my best. So just to recall, we have two integers, two probabilities, and I'm looking at two shifts, full shifts, and these are called Bernoulli schemes, recall. And the claim is that if their entropy is the same, then there should be an ash-homeomorphism that conjugates them. Recall that this meant that there's so this is a partially defined function such that it is defined on a full measure set. And on that full measure set, with respect to the subspace topology, it becomes a homeomorphism onto its image that is also full measure. And of course, the other way around is straightforward. And this was the definition of entropy, Kolmogorov-Sinai entropy. So we have a bunch of different cases here. Okay, so now I'm starting really the proof. Of course, if A is 1, that means that the first system is trivial. And that means that so the entropy ought to be 0. And the only way that can happen is the other one, the probability for the other one is also a delta measure. That is to say, only one of these components is 1. And so this row is okay, and this column is okay. In this case, based on straightforward, calculus arguments, you can realize that the entropy can be equal only when you have a homeomorphism that is defined everywhere. This is also straightforward. This next case is this part. That is to say, one of the symbols, one of the shifts have two symbols, the other one has more than two symbols. The argument that Keane and Smorodinsky give also work for this case, but you need to do some adjustments. So I'm just going to skip this case so that we're in this case. Okay. So assume A and B are at least 3. Okay. So the first step is using an argument that is, so it's based on, I guess it would be appropriate to call entropy flexibility for Bernoulli schemes. What you do is you take these two vectors, and the first step is to match one of their components. Lemma. There is a C and there is a probability on it. Underscore, recall, meant the set with C elements, such that first of all, the entropy is the same. I'm assuming that the entropy of P and the entropy of Q are the same. Entropy is the same. There is some I such that R0 is equal to P0. Sorry, Pi. And then there's some J such that R1 equals 2J. So somehow this intermediate vector that you come up with has one component that coincides with some component of the first vector and some other component that corresponds with some component of the second vector. And so this comes from proof by entropy flexibility of Bernoulli schemes. And by this I mean that there's a straightforward argument that says that given any eta, you can find a Bernoulli scheme with that entropy. So whatever argument you use to verify this also gives you this. So based on this, we can say that up to a permutation, P0 and Q0 is the same. So based on this, from this, let me write it over there. Okay. So that is to say, the probability of occurrence of the zeroth symbol in X, the first space, is the same probability. Or at least I can assume this. And this zero symbol is going to be a marker for me. Okay. So because of this, 0 is going to be a marker. And I want to have my ash-homeo to, at the very least, take the 0 symbol to the 0 symbol. Or if you want, the sequence that is all zeros to the sequence that is all zeros. And whenever you see in any point here a 0 in some component, you want the image to have the same 0 at the same place. So this sort of gives you something like a frame for your ash-homeomorphism. Okay, so this is the first step. Okay. So this also, you can realize, defines a common factor for the both systems. That is to say, if I were to say, for instance, O, this is going to be my marker, and you can imagine this to be a hug as well, and X, this is going to be everything else. So 0 symbol, I'm going to send to O, every other symbol from either space, I'm going to send to X. In other words, kiss. So everything else. Okay, so this is a two-symbol shift. It's going to be, but so let me send A to kiss hug, 0 to O, else to X. And likewise, I'm going to do the same thing with B underscore 0 to O, everything else to X. Okay, so this induces factor maps from X to the shift, full shift on these two symbols, and likewise for Y. So this induces, let me write it here. This is P hat sigma X, Q hat sigma Y, and then a common factor. Let me call it just sigma. And then what's going to be the probability here is going to have two components, PO, which is going to be P0, and PXP kiss is 1 minus PO. And this is called the marker process. It's also, of course, just a Bernoulli scheme, but and this statement here means that I want to build my ash-homeomorphism here in a fiber-preserving manner. Okay? So this is step 1. Step 2 is to start building some combinatorial structures that allow you to handle the fibers. Essentially, you want some control over the fiber entropies. And the combinatorial structure that you use is what's called a skeleton. And it's just going to be a certain type of word in kisses and hugs. And then once you figure that out, and after proving a couple lemmas that tell you something about the sizes of certain sizes of sets that represent certain skeletons, you apply this structure, societies, etc., that we discussed last time to start building this phi one step at a time from one skeleton to the other. Let me define what a skeleton is. So the idea is always that you see, in the context of societies as well, you overcount first, but you just associate some set to any point, and then you sort of refine it to get a coupling. And it's sort of like the same idea. You always overcount, and then you reduce. This is the idea. Definition. Let me take R and L, two integers, and I'm going to call skeleton of rank R and length L is, so skeleton S, is a word in kisses and hugs of this form, of the following form. I'm going to do something slightly different from what Keane and Smorodinsky do, but it's the same. It's equivalent. I start with a kiss. I have a bunch of hugs and then a bunch of kisses. Like this. So you alternate between, so you start with one kiss here and one kiss there, and in between you're alternating between sequences of hugs and kisses. So this I'm going to call the end hug, this too. And the middle sequences of hugs I'm going to call mid-hug. And this is the end kiss, mid kisses. All right. In such a way that, and this is where the parameters come into play, the length of either end hug is at least R, and the sum of, so the total x's, total kisses, is exactly L. So in your skeleton, you have L, exactly L spaces to be filled in. X marks places that you need to fill in. And hugs tell you, so you have sort of like a large sequence, initial sequence that tells you this is where my skeleton starts. And then in between, you still can have hugs, but it can only be less. So either end hug has to have at least R, and any mid hug cannot be longer or equal to R. And mid kiss equals L. Okay? You can write this in a more explicit manner as well, but let me just leave it like this. But it turns out that this is not quite sufficient. You want to be able to fast forward this a little bit. So instead of just leaving it like this, you say also, you take a sequence that goes to infinity, and then you call a skeleton S is an n rank R skeleton of length L if it's a rank n sub R length L skeleton. So R is an integer, I'm imagining this to go to infinity, 1, 2, 3, 4. And n sub R is also a sequence of integers that possibly go faster than R does to infinity. Okay? So examples. Rank 1, for instance, means that you don't have any mid-hugs. This is an example. So is this. And so on. But you could have n hugs larger than 1. If you wanted, you could have done this or this. Okay? All of these are words and kisses and hugs, and each of them is a rank 1 skeleton. This has length 1, length 2, length 3, 1, again 1, and so on. I should mention that the rank is not unique. So for instance, this is a rank 1, length 1 skeleton, but it's also a rank 2, length 1 skeleton. Okay? This is the idea. So the important thing about this is that you define these because if you were to see this block of code in your Word, if you were to shift this in any way, it would have empty intersection. So this gives you a very nice combinatorics. That's the first thing. And then the second thing is that if you were to increase R, if you were to start with a rank R skeleton, you would be able to decompose it uniquely into rank R minus 1 skeleton. Rank decomposition And I'm just going to give a proof by example. Okay, so this is a rank 3 skeleton. I started with 3, as you see. I'm saying this is where my skeleton starts. This is where it ends. In the middle, I have hugs, but none of them have length 3. Okay. So now what is the rank 2? So rank 2 decomposition for this? Well, I can say this. This is 1, then 2, 3. That's the rank 2 decomposition. And then the rank 1 decomposition of this is this. This is still rank 1. But you see now I cannot go all the way because I have this. Now I would need to split it like this. Okay? This is the idea. So now a lemma that tells you some further things. Let me clear here. Okay. And so I'm going to say that I observe I observe a skeleton in a word in an actual point in X. If I see a part of my point in X that is fitting into this skeleton. So this means that, for instance, so let's say that X is like this. So let's say 0, 1, 2, 0, and then this is also 2, and then you have 0 here. I'm just looking at the finite block of it, and then the associated skeleton for this would be hug, kiss, kiss, hug. Of course, it has a growing sequence of skeleta that fit into each other. In this case, there is more than one skeleton that X fits into, or that fits into X. But if your 0th entry were not the marker symbol, then there would be a unique skeleton for any rank. Let me write this. Let me write it like this. For almost all X in X. Yes?
Can you use that, let X interpolate?
This is good?
But also the elements.
It's small. It's small.
But it's also the kiss, right?
Yes, but it's large. I mean, I could have done zeros and ones, so I decided to do this. Yeah, P. Well, omega. Okay. For almost every word, almost every sequence in omega, for any integer sequence that goes to infinity, and for any R, there is an n rank R skeleton. Let's denote it by S sub nr of X. And if the zeroth coordinate of omega is not 0, then this is unique. No, that's why. So if the zeroth coordinate is 0, there are many skeleta that you can put in, because it just hits into one of the markers, and you're not controlling the markers at this point. But if it's not 0, then you just sort of start reading your word to the left and to the right, and you're counting, then you're switching to markers and hugs and kisses. And based on that, it is sort of, and once you fix the rank as well, it gives you the unique skeleton. If not, then there are multiple. So yeah. So okay, this is the first one, and then the second is that for all, I'm gonna write normal text. Okay, for all sequences that go to infinity, and this is going to be the second parameter. This is going to be the length parameter, if you want. And for all n that go to infinity, for all omega in omega, there is an R naught such that for all R larger than R naught, sorry, I don't have this actually. For all length sequences, for all rank sequences, there is some large enough R such that after that, if you were to look at the skeleton, such that its length is at least R, this has full measure. Okay. Yeah. Okay. Oh, sorry, this should be there exists. If I fix a length sequence, I can find a rank sequence, so I can fast forward my skeleta such that for large enough parts of the system of skeleta, I have that the unique skeleton has length at least L sub R. So for almost all points. Okay, so these two are going to be the parameters. And the idea, let me say, is that so from something else, we're going to get what this L should be, and that something else is going to be the Shannon-McMillan-Breiman theorem. And once you have this, it's going to tell you the increasing rank sequence that you should be using. Okay, so this is that. And this is just Borel-Cantelli. This is by Borel-Cantelli. Right, so this is what is this? This is a lim-inf really, lim-inf of these sets. I'm taking the lim-inf. You can just show that one of them has, or the complement of one of them, a large for a large R is 0, etc. So straightforward measure theory arguments. Okay. So this is the skeleton that we're going to be using. And the next up is the fillers. You don't touch hugs, and you're trying to figure out, so once you have a skeleton like this is where this method shines, I think. Because this also can be interpreted as a couple of cylinders of the marker process of the common factor, we can also interpret this as telling you something about the first system, omega, and the second system, y. And so this is where, this is why this is useful. You said that, so you're saying that my ash-homeomorphism should preserve the hugs. Okay? So now you have these spaces that you need to fill in. Once you have this in the first system, based on some arguments, you need to figure out where to send it. And this is where the idea of the society comes into play. But before going into that even, let me just say a couple more words. So I can interpret my probability vector to be a point in the simplex. And so now let me define a new probability on the set that contains everything but the marker. Okay? So this is just P0I is going to be Pi divided by 1 minus P0. Let's assume that P0 is not 0, is not 1. So geometrically speaking, if this is my simplex of probabilities, and if, let me just draw it like this. If your probability is here, you look at the projection here, and then you extend it so that you get another probability. So if this were P, this were P naught. Okay? And so this is called the filler alphabet. Filler probability. And likewise, its H is the filler entropy. That's to say fiber, if you want. Fiber entropy. Okay? So now, you see, this entropy too is going to be matching. So H of P0 is going to be the same thing as H of Q0. Because of our assumption that the zeroth component of P is the same thing as the zero component of Q. So they're going to have, the fillers are going to be also the same. Okay, so now, now we need more combinatorics. Okay. I don't think I'm going to do a good job explaining this next part. So I'm going to have S a skeleton. Let me denote by F to the omega of S the fillers of coming from omega. That is to say, this is a certain set of finite words, and the symbols coming from here, where you put them into the into the spaces of x's. Okay? Coming from, let me just write it like this. Fillers of S coming from so take symbols from the filler alphabet A underscore take away 0, put them in x's. So it is bijective with with a set of words. So this is the length of the skeleton into A underscore take away 0. It is bijective, but given the skeleton, its hugs are at certain places. So in a sense, because you're attaching this to the skeleton, you're encoding a place information as well. But it's a finite set. It's a finite set of words in the filler alphabet. Okay. So now I want to define an equivalence relation on it. And the way you do this is by a certain, so if you have a set of words, and if you want to define an equivalence relation on it, one way to do this, a more straightforward way of doing this, would be to say, I'm just going to look at certain places, and I'm going to say two fillers are the same if they are the same at those places. So if their restrictions are the same. Okay, so that's a standard way of defining an equivalence relation on a set of words. Where you should be looking at is going to be dependent on the entropies. And so that's for that, you're going to need something like a stopping time. And because of that, so this is exactly where the Shannon-McMillan-Breiman comes into play. Okay. You want to define an equivalence relation on this, and as well as on f to the y of s. Say you have a subset J of S of, oh, this should be, let's say, over. So this is a set with L of S elements. In this set, and put F1, F2, two fillers, two words. If, first of all, oh, sorry, this should be a filler. Say, for all F, for any filler, you have a certain place or a subset of your indexing set. If, first of all, the indexing sets are the same, and if I were to restrict either one of these fillers to this indexing set, let me just call it J, on it, they are the same. So I can imagine a word to be a function from this finite set as well. I'm saying two functions are going to be equivalent if there is a certain subset in their domain such that on it, when you restrict both of the functions onto that subset, they have the same function. This is how you define it, and it turns out that, so we're going to figure out what this subset is based on entropy considerations. Comes from entropy considerations. Considerations. You actually start with the first element, right? So let me just write this explicitly. For any filler, J is fixed.
And you're going to tell us how to do it later?
Yes, I'm actually going to do it now. Say for any filler, there is a J. So this set is this. So this is how you define J of F. You take your filler, okay? Let me give an example, perhaps it's going to be better. There is this. You take your filler. So I can imagine this to be something like this. F equals F1, F2, F else of this. Each of these is a filler symbol, and they're ordered. And the fact that this is a filler for S means that if S were kiss, hug, hug, kiss, kiss, etc., means that I'm putting the first symbol to the first kiss, second symbol here, last symbol to the last kiss that is in the middle. Okay? Start reading off from the left these symbols. And you sort of keep taking more indices insofar as their measure is not below a certain threshold. So fix, let me say it this way. Fix and epsilon sub r positive, tilde. Epsilon sub r tilde positive. And say that J sub f is the set of all those entries or all those indices I in my index set, such that if I were to use the filler probability, let me write it like this. So here's the thing. So I'm looking at the probability of this symbol, okay, with respect to P0, my filler probability. And then I'm saying, is this larger than, more or less than this epsilon? If it is, then I keep going. I take another one. Now, all of these probabilities are less than 1, which means that it keeps decreasing, or it's not increasing. And eventually, you're gonna be lesser than this. But until you get to that threshold, you keep taking more indices. Okay, that's the idea. Let me be more explicit here. Let me just write it like this. So P0 of F1, P0 of F2, P0 of Fi is not lesser than my threshold. Okay? So there's going to be a maximum here. You're going to have a maximum index such that all the previous indices are here. Okay? So you're just taking the first part of your filler. However much, that depends on this filler probabilities. Where does this come into play? Or where do you get that epsilon r? Well, you get it from Shannon-McMillan-Breiman. Okay? So, I mean, this still defines an equivalence relation, but it's just that it doesn't, that equivalence relation doesn't necessarily work for our purposes. And of course, the equivalence relation here that I defined is going to be dependent on what this number is. And R is the rank of the skeleton. Okay. Okay, I have 13 minutes. I want to mention, where does this epsilon sub r comes into play? Because I want to be able to do this in such a way that as I'm increasing r, because of that r is the index of my length sequence or the rank sequence n. And so as I'm increasing it, that sort of represents taking larger and larger skeleta that fit into each other in such a way that if I were to look at the larger skeleton, it has a unique sort of smaller subskeleton based on this decomposition that we discussed. So I'm just going to state a certain version of SMB theorem. And I think this is called the, what is it called? Entropy equipartition. Entropy equipartition property. Okay? So, let me just state it generally. If you have an ergodic system, there's an arbitrary x, m, ergodic. And let's say that its entropy is finite. We discussed a little bit last time at the end how this entropy can be interpreted as the average of a certain information function. Well, in a sense, this is just telling you that you have pointwise convergence. Let me be more explicit. So here I'm going to denote by, so let's have alpha be a finite partition, be a generating partition, generating partition. Recall by Krieger, because entropy is finite, this exists. Which means that if I were to take this and if I were to refine it using its images under F, I would get the whole sigma algebra. Then for all epsilon, there is an n for all n larger than n. This refined partition up to time n. So this is of the time n of alpha. This just means alpha refine, pull back, refine x squared all the way up to n minus 1. If you want, this is a cocycle over the pullback operator on the space of partitions. So this is split into two categories. So let me write it like this. It is a good part and a bad part. This is bad. And of course, it depends on epsilon, n, and f. Let me not write those. In such a way that the bad part, so the total measure that is covered by elements in the bad part, is less than epsilon. And if I were to take any cell in the good part, its measure is comparable to e to the entropy of the time n. This is just a lower level statement of what I just said before. It's a certain entropy, so it's just saying that a certain information function is converging pointwise almost everywhere. Such that mu of the union of all those bad cells is less than epsilon. And for all cells in the good part, so the measure of the cell is bounded from above and below by e to the minus n entropy minus epsilon in here. Minus n and f plus epsilon. Okay. Of course, in information theory, we put here a 2, but I'm counting entropy in nats instead of bits, so I'm using e. Okay. So how do you use this? Well, you have a sequence R that goes to infinity. For each R, I'm going to do something. Yeah. So now fix. Okay, so I'm just going to use this equipartition property. Okay, so of a small measure set, I have a nice partition given by refining the generating partition using my dynamics. The measure of my cell, or of any cell, is proportional to n times entropy, logarithmically speaking. This is also telling you why entropy formulas should be true, actually. So now take a sequence that goes to 0, parameterized by R, let's say, and let alpha be the standard generating partition of 0 cylinders, be the generating partition. For for the filler system. Something start. Okay. Then for all r, there is a time k sub n sub r, such that for all n after that time, or maybe I should have used k actually. Let me just use k to be safe. For all k, if I were to look at the refined partition, it splits into a good part and a bad part, such that the bad part has measure at most epsilon sub r, and for all g in the good part, this is bounded from above and below by so minus k entropy of the filler minus epsilon, and here e to the k entropy of the filler plus epsilon. And essentially, this is epsilon sub r, and this is my stopping time. Okay. So, and of course, these partitions, as you see, I'm taking a finite refinement of my standard cylinder, which means that I'm just taking a block code that is finite, and I'm saying that of a small measure subset of block codes, I have this very nice estimate. But of course, these can be interpreted as things that something that tells you something about the fillers as well. Eventually, you're going to possibly fall under this bound, or this bound, whatever. And based on this, now if you were to define equivalences, so the equivalence relation between two fillers using this bound, it works. Okay, this is the idea. 2 minutes. Okay. So we have now a machinery. Okay. We have a sequence epsilon dot that goes to 0. Based on this, we have another sequence epsilon sub r, or epsilon dot tilde, that also goes to 0, but in a way that is compatible with entropy. Given by this. Now from this, recall that in the skeleton lemma, or lemma about skeleta, we had something that said, based on an increasing length sequence, I have an increasing rank sequence. Well, I'm going to choose that length sequence to increase in such a way that is compatible with the decrease here. And this is how you find the parameters that you should be using. Okay? So, okay, I'm running out of time. Let me just say one final thing as to how this matching works. You start with a skeleton. It has its filler set, its equivalence relations, everything. You write it. This is rank n r. You write it as, I'll just write it like this, as 2, as skeleton of rank 1 less. Okay? And so now, inductively, you can compare the equivalence relation here and each of these equivalence relations put together. So one of them is coarser than the other one, but based on which one is more coarser, which I'm going to mess up, that's why I'm not saying, based on which one is more coarser, you're defining, so from this, you get a society. Okay? From the fillers of omega with respect to s, or rather up to sigma, up to tilde, to the fillers of the other guy. Then you apply marriage lemma to get a coupling from this, like we discussed last week. And when your R is odd, you go one way. When your R is even, you go the other way. And so this sort of allows you to basically zip the two dynamics together along the fibers. I wish I could say more, but I think this is all I want to say today. And this is the end. Thank you. Yeah, sorry, I couldn't finish this. Oh yeah, sorry, I had a clarifying question. Like I said, the person left. Oh, John answered. Okay. Oh. Exactly. Yeah. So yeah, exactly. It's that simple. Okay. Oh.
I think it was ambitious to do this in 3 lectures.
Well, yeah, it's a 10-page paper, so I thought. Yeah. No, yeah, I think I miscalculated how long it would take me. And of course, I got distracted with the cohomology equations and all that stuff too. But at the very least, I mean, I hope at least the grad students got something out of this. Bunch of different things. It's just that, and unfortunately, this is also like perhaps the issue with combinatorics. I'm not very knowledgeable about combinatorics, so it takes me quite a while to understand. Yeah.
So is the idea of the proof at sort of the biggest level possible? You want to reduce sort of this dynamical, infinitely divisible situation to a series of discrete problems.
Yeah.
And you want to solve those problems in a compatible way so that you find a limit in the end.
Not only discrete, but finite.
Finite,
Yeah.
But it needs to be also compatible. So then you have well-defined maps. And to make things, so if you only wanted to define a factor map,
Yeah.
then the idea is to use the equipartition property to always give yourself sort of extra room in where you're sending things and be able to predict the size of these things. This makes compatibility very nice. Now, however, you want a bijection. So you need to alternate back and forth.
Yes.
So that the cylinders you're sending them to at half of the scale, you know where they're sending them to. You're sending them to a unique place. And in the other half of the scales, there's a unique set of guys going into them. And in the limit, this will define a well-defined bijection almost everywhere. Is that sort of at that very top level what's going on?
It's almost like you know it better than I do. No, it's like it's great. Yeah. Yeah, I'm still not super comfortable with all this stuff to be able to summarize it the way you could. So, but I think it's a great summary of what is going on.
I think we should all thank Alf again. He gave 3 fantastic
Yeah,
lectures.
thank you for joining.